Hi there. In the last video, I have pitched a solution which helped me to decrease our heating bill. As I promised, the project will be open sourced as much as possible. In this video, I will show you the schematic, the PCB, and the box which I've created. The circuit starts with an RJ45 connector. However, this is not just a simple connector because it includes the built-in transformers with a Bob Smith termination, which allow me to save several components. The DC voltage is present on the VC1 and 4 of the connector, while the TD1 and TD2 differential pairs are required for Ethernet operation. The DC voltage coming from the connector is routed to a full bridge rectifier, which ensures that the miswired cable or an incorrectly assembled patch panel cannot cause reverse polarity for the rest of the circuit. The PoE functionality is handled by the TPS2375 IC. This IC has an integrated low-side switch and it features a fixed 450 mA current limit with a programmable inrush current, which is set via resistor R6 according to the datasheet. This means around 140 mA inrush current to support legacy PSEs. The next noteworthy component is resistor R4. According to the datasheet, this resistor assigns the device to class 4 unless the switch has these settings pre-configured. The third and final important resistor is R5, located in the detection pin. This value is selected assuming two full bridge rectifier. After the circuit powers up, no current flows through this pin, but it's critical during detection as the switch uses this to recognize that the PD device has been connected. The PG pin is an open drain output that becomes active after the inrush current phase, signaling that the IC is operational. As a result of the above, the circuit uses two different ground potentials. The regular GND extends from the full bridge rectifier to the PoE IC, while the rest of the circuit uses separate ground labeled PSU GND. Unfortunately, I received conflicting information regarding whether the metal housing of the RJ45 connector should be tied to the regular GND or PSU GND. I choose to connect it to PSU GND at the end. The next page shows the switching mode power supply. I don't think we need to deep dive into the details, as this is a standard design following the datasheet and common sense. As you can see, there are two of them. The 24-volt unit powers the valve regulator, while the 5-volt section supplies the microcontroller and its surrounding circuitry. The third page of the circuit has the microcontroller and the Ethernet IC. The schematics also includes a linear 3.3 volt regulator, a clock generator required for the Ethernet IC, the output switching MOSFET, two reset circuits, here and here, and also two connectors which are necessary for programming the ESP32. This programming enable should be short-circuited until the first programming finished, and the ICSP header needs a proper USB to serial converter which supports the 3.3 volt. Since those connectors are usually only used once, because the further programming is done from Home Assistant via the network, I did not solder in the connectors, just plugged in the serial converter and did the first round with friction connection. So the PCB is designed with 4 layers. The top layer carries the traces for both digital and analog circuits. The inner one layer is entirely dedicated to PSU GND. The inner 2 layer is also mostly PSU GND, but it also holds the traces that I couldn't route on the top or bottom layer. The bottom layer is primarily PSU GND as well, with the exception that the Ethernet connection pins exits the connector here, and the DC voltage also tapped off from this layer. This is done mainly because I wasn't sure when I first used this RJ45 connector, and I wanted to make sure that I can cut these traces if I messed up the order of the cables for the Ethernet communication. So it was bulletproof, but it's working, so I can move these pins to the other layers if it's needed. Additionally, in the top left corner, there is a separate section dedicated to the 3.3 watt regulator's cooling, allowing it to dissipate some heat through the bottom layer. This is the 3D model of the board, which was shown in the last episode, so I don't want to spend much time here. The programming header with the prog-enable jumper and the dummy load resistor will not be populated, and I also skipped the green output connector, soldering the wires directly, but as I found out later, that was a mistake. Here you can see the box which I've designed for the controller. There is a cutout for the RJ45 connector and the cable of the valve, and also some cutout under the parts which need soldering on the bottom layer. Here you can see a few images of the already working controllers with both horizontal and vertical holders. If you watched my video so far, it is time to direct you to the resources which are already available. The GitHub project contains the local copy of the electronics and the STL files for the 3D models, but you can get the project files from OSH VLab too. The links can be found in the description as well, under my Patreon information, where you can support this project. And as I promised, YouTube bitching is imminent. Don't forget to like, share and subscribe and hit the notification bell. And as always, let's keep the smoke inside. Bye bye!